into strain transformation. Similar to stress transformation, since strain is also a tensor of order 2, they follow similar pattern of transformation as stresses, right? So in the beginning itself, I'll tell you that if you have a tensor of order 2, the transform tensor, epsilon in a dash configuration will be given by your transformation matrix into your strain matrix, right? That you have into again your transformation matrix. I think one of them will be transpose, right? So the same thing that we did for stress. For stress also we did the same thing. So mathematically speaking, they remain same, but we need to understand how we develop these equations and how to get into it. So the part of the course that is there is what I'm reading here. Okay, I'm reading some. This one is supposed to be right, or no, problems are done. Yes. So this is what. So what we have to do is, these are the part of the syllabus. First is strain transformation, then principal strains and maximum modes, maximum shear strain. Okay, and their planes. These are part of the syllabus. This is what we'll cover today. And in the next class, we'll cover mode circle and strain measurement. Okay. For strain measurement, we use something called strain gauge. Okay. So this is what a strain gauge look like. This is mostly a piezoelectric material. So a part of piezo composite. And what happens, piezoelectric materials are generally they work in multiple domains. So if you give a mechanical stress to it or mechanical strain to it, it will provide electrical output. So you will see that a piezoelectric material with a lot of electrical circuits inside circuit, and those will come out as electrical, and then when you connect them with the power output, you get the voltage out when you put an electrical strain to it. We'll discuss this a little bit more in the next class. But this is a material in which you get electrical circuit, so that when the material gets strained, they provide electrical voltage output which you can tap and provide it as output of the material, and from that voltage you can calculate the strains. So that's how a strain gauge work, roughly. I have explained. So we have learned about, in the last class, we have learned about normal stress and normal strain and shear strain. We know the normal strain is a change in length, while a shear strain is a change in angle. Okay, and then you do a ratio of the normal strain with the actual length of the member, then you get the strain of in that direction. So our objective is, if I know strains along any one set of axes here, like x and y, how do I find strains along a different axis? That's our objective, right? Please note, the derivation is not going to be as simple as we did for stresses, because in stresses we assume things to be independent, right? But for strains, things, if you elongate in one direction, it will give rise to not only elongation in that direction, but deformations in other directions also. For example, let's say there is this is an element, undeformed element, O, A, B, and you can put this as C or D, whatever you want. Now, line OA and line OA and OB are perpendicular to each other, right? When you give a stretch along x-axis, so when you give a stretch along x-axis, the line OB will move to a little bit extra, right? Which will be given as epsilon x dx. Epsilon x is the strain, and dx is the original length, right? So the change in length is epsilon x dx. That's clear? Okay. Similarly, along y, it is OB. Okay. How do you get O? That one. So epsilon x is change in length. So I will write OB dash minus OB, right? Divided by OB. Let's say this is B dash. Okay. So OB dash. So this becomes OB dash minus OB equal to epsilon x into OB. Now OB is dx, right? We all know. So change in length Let us name it as delta OB is equal to epsilon x. So this is what is written here. Similarly, I can write this part, the vertical part. If there is an elongation along y direction, I can write that as epsilon y dy. Okay, clear? Now you need to rotate that element also, because there will be a rotation in that element. Now that rotation, because of shear strain, there will be a rotation here, which is given by gamma x by 2, gamma x by 2, and therefore this point, which was in elongation a become a dash, will move to something here because of the rotation of this element. Similarly, b, which has moved to b dash, will move to somewhere here. Now you can draw a parallel line up to this and parallel line about this, and they join here. So this point has moved to that point. Okay. So we will now, our objective is to calculate all these values when you do a transformation also. Clear? This is what I have explained is given here. So along x, it is OB dash. So it becomes, this is, if this is a length, this becomes a into epsilon x. This becomes b into epsilon y if this is b. And this is your shear stress angle. Remember that we cannot give on both directions. So we given, even we can give it in one direction. Okay. All right. Now let us look at a few definitions, that few things that we need to note. One is anti-clockwise theta is positive for us. So any rotation that is anti-clockwise is positive. And we know what is a positive shear stress and positive normal stress, right? Positive shear strain and positive normal strain, right? Positive normal strain equal to elongation, right? Positive shear strain is less than 90 degree. Resultant angle, okay? Resultant angle is less than 90 degree. All right. And counterclockwise rotation in your plane is considered to be positive. So we are looking at here also a 2D plane transformation. Okay. So objective is you had an axis which is x and y. Now the axis have rotated to x dash and y dash. So that's, and the angle of rotation is theta. We will draw more circle in the next class, and same things follows, same rule follows. So what we are doing now is, let's say we had an element along x and y axis. So this was my element along x and y axis. Okay, this was an element along x and y axis, and I'm putting that x dash and y1, x1 and y1 axis along the diagonal of that element, just for the sake of simple resolutions. So I have put that. So this is my original ds element, right? Okay, now we are looking at how much this element has elongated. This element is rotated at an angle theta, right? So if I look at elongation of this element, I will get the elongation along x dash axis, right? Because my x1 and xy1 axis are rotated axis. So if I can find elongation along this axis, this diagonal element, I will find my elongation x dash, epsilon x dash, right? So this is my elongation along x, and this is my elongation along x1, right? So if I put my x1 axis along the diagonal, and if I can find how much the diagonal has elongated, I will find my normal strain along x1 axis. That's the whole objective, right? Now normal strain along x1 axis. So this diagonal, as you can see here in this picture, the change in diagonal from here till here, right? The change in diagonal is not only because of elongation along x, so not only about epsilon x, but also due to epsilon y and gamma xy. So the elongation here of change in length of this diagonal has been manifested by three things. One is epsilon x in the original configuration, by epsilon y in the original configuration, and gamma xy in the original configuration. All three will contribute to the change in length of the diagonal. Okay. So let's first look at due to x directional motion. What happened? So if I have an elongation in the original x direction, so not in x dash, okay, original x direction, if I have an epsilon xx, how much it contributes to the change in length of the diagonal. All right. So due to change in, so this element now has moved to a new element because of only epsilon x, right? So if I give only epsilon x here, so it is going to move along this direction, right? Other two are 0. So this length, this width is going to remain same. Only thing, the length is going to change to a higher length like this. Okay. Now you see what happens to the diagonal. So initially the diagonal was this, and the diagonal now moved to here. So point O remains at O, point D remains at D, point B moves to B dash because there's an elongation, point C moves to C dash. Okay. And CC dash and BB dash are parallel because there is no other extension, only extensions along x-axis. So therefore, your C moves to C dash, therefore OC has moved to OC dash. So the diagonal has moved. Now change in length of the diagonal is going to be given by C dash, C double dash. If you put a diagonal perpendicular from here like this, so this is the change of length due to change in this length. So how much is that change in length? You have to just calculate it, right? It's a geometry. Okay. So CC dash is equal to BB dash, and that is going to be epsilon x dx, right? BB dash, we have just defined that BB dash. This change in length is going to be epsilon x dx. So this is now known. This epsilon x dx is now known. Once that is known, I have to find this. And what I know the angle, right? This angle is known. This angle is theta angle. So if that angle is known, that length is known, right? CP is known. So CP, this angle is theta. So CP is given by C dash, C double dash. So I need to know this. So if I know CP, I can know this. So CP is going to be this into cos theta. And what is this? C dash, C double dash? C dash, no, this one, C double dash, C dash is BB dash. So that's what I have written here. So that picture is drawn here. So it is epsilon x ds into cos theta. So the elongation of ds, this is my ds length, elongation of ds is given by epsilon x dx cos theta. Okay, that is only because of elongation along x-axis. Now, what happens if you have elongation on y-axis? Because the diagonal change will be because of elongation along y-axis also. Let's see it. So let's say this is my original element, and there is only an elongation along y-axis is given. So epsilon y is given, others are 0. So now the diagonal used to be this, which has now moved to another diagonal, which is this. Okay, please note, while it moved from this diagonal ds, that means OC to OC dash, it has made a rotation also. That rotational angle is alpha. So we are not going to talk about right now this, but maybe after 3-4 slides we have to talk about. So there is an change in angle also, and it is obvious. So now this length is, let's say, dd dash. So dd dash is going to be epsilon y dy, right? And which should be equal to cc dash here because they're parallel lines. I need to find c dash, c double dash. So this is what I need to find. If I draw a perpendicular from here, this becomes an arc length. So these two remain same. I have to just find this one. So that comes out to be, if you do the geometry again, it's comes out to be epsilon y dy sine theta. So epsilon y dy sine theta is the elongation in the along the line of epsilon dash x, right? So this I will write elongation along x dash line of ds length due to epsilon y acting on x dash axis, right? Same thing I can write for this epsilon x dx cos theta is elongation along x dash line with length ds, right? Due to elongation epsilon y, or due to strain epsilon y. Sorry, not epsilon y, epsilon x. Okay, right? So 2 I got, but now there will be a shear strain, right? There will be a shear strain. Also here, also you please note that there is a change in angle, and that angle is alpha 2 for this case. Okay, now what happens when you have shear? All right, so you give a shear to the element, only shear to the element. So this is your element, again the blue colored, and this dash lines represents the change due to the shear, right? So this becomes something like that. Okay, and this angle is gamma xy, that is the shear strain that is given. All right, and now this angle was theta, which will now change to another different angle because the diagonal was used to be OC, which has now changed to OC dash. What I have to look at? I have to look at this much elongation, right? C dash to C dash, this elongation. And I know this elongation because once I know gamma xy, I will multiply with this length and I will get that elongation. So CC dash, so DD dash is gamma xy dy. So therefore CC dash is also going to be gamma xy dy. Therefore C dash, C double dash is going to be cos theta. So it is going to be gamma xy dy cos theta. Okay. Now let us look at here in my original configuration. In my original plane, axis xy axis, we had epsilon x, epsilon y, and gamma xy, right? Okay. So the contribution of all this will be there in epsilon x dash. So what I'll do, my total elongation of that element, total elongation of the elemental line, what was the line? Diagonal line ds along its axis, along epsilon dash axis, right? Epsilon x dash axis. No, epsilon not, will not epsilon x, we'll write x dash axis, right? X1 axis is going to be summation of all those things because all of them are elongation, right? There was no change in length, reduction in length. All of them are extension in length. So delta D is going to give you this is due to change in epsilon x, epsilon x, this one. This is due to change in epsilon y, this one, and this is because of the shear gamma xy. Okay. Now you add them up, so you get total change in the length. So total change in the length is this, adding them up, and therefore length per unit strain along that direction is going to be change in length divided by original length, which is ds. So it's going to be something like this. Now we can write dx by ds as cos theta, dy by ds as sin theta, and so on and so forth, right? So this can be written as epsilon x1 is going to be epsilon x cos square theta, epsilon by sin square theta, gamma x sin theta cos theta, which if you do a little bit of algebra here, trigonometry, you can get something like this. And you see this formula is same as what you got for change in normal stress. Only thing is, note, there it was only gamma xy, here it is gamma xy by 2. Why is 2? Because rotations, transformations of stresses or strain depends on mathematics or tensor transformation, right? And gamma xy is engineering strain, not a tensorial strain. The tensorial strain is gamma xy by 2, and therefore that gamma xy by 2 will come. All right, clear? So this is how you find epsilon x1 or strain along x1 direction in a rotated coordinate system, if you know the strains in the original configuration. Now, how to find shear strain? Okay, shear strain. So shear strains we have already found, right? So due to epsilon x, the shear strain changes alpha 1, and I can calculate alpha 1 if I know C1, C double dash, which is known, right? Because if I know this, I can know this. It's very easy. It will be the sine component. That was your cos component. So this is going to be this was your cos component. So this is going to be a sine component. That divided by the length will give you this angle, assuming that's very small. So alpha 1, remember this alpha 1 is clockwise, right? So this was your original one, and it has moved to something clockwise direction. Similarly for this one, for epsilon y, it has gone up, right? So it was anti-clockwise. Remember this, it has anti-clockwise. Alpha 2 is anti-clockwise. And we know how to find this length, right? We have already done it. And then normal strain due to shear, it's going to be again alpha 3, which is along clockwise. So that's also going to be negative. And we have to find this C dash, C double dash. So once you know this is the cos component. So this is going to be a sine component. Here we know that this is my sine component. So this is going to be my cos component, right? So for shear strain, tan alpha 1. So this is what we are doing, tan alpha 1. This is because of epsilon x dx. Tan alpha 1 is going to be this guy divided by ds, the length. Now that guy is epsilon x dx, sine component, as I said, divided by ds. And this is clockwise. Okay, please note that. Similarly for epsilon y, this is what we need to know. And we know that this is sine component. So this is going to be my cos component. So this is epsilon y dy cos component, and that divided by ds is the alpha 2, tan inverse of alpha, tan of alpha 2. And since alpha 2 is very small, we'll assume it to be tan alpha 2 is alpha 2. This is what I've written here. And alpha 2 is counterclockwise. Similarly, we have to do for this, and this is also clockwise. Now, when you add them up, remember you have to add them up by looking at the clockwise and anti-clockwise. So clockwise is negative for us, so minus alpha 1. Anti-clockwise is positive, so plus alpha 1, and this is again negative. And you put those values back, what you get alpha, change in angle alpha, is going to be minus epsilon x minus epsilon y sine theta cos theta minus gamma xy sine square theta. Okay, right? But note, change in only along x-axis is not your gamma xy. Your gamma xy is changed due to both x and y axis, so both can rotate, right? So it is not only addition alpha, it is alpha plus beta. The beta will be on the opposite 90-degree angle, right? Beta will be due to change in y-axis. We have looked into all changes due to ds along this diagonal. We have to look into all changes because of that diagonal also, right? Shear strain changes. And that you find by putting theta plus 90. Remember, we did it for stresses. So that you find putting theta plus 90. So you get this. All right. Now you have to, your shear strain is given by gamma xy is given by alpha plus beta. So when you do alpha plus beta, you get something like this. Okay. All right. So this can be sine 2 theta by 2, and this can be cos 2 theta by 2. So that is your change in shear strain. So this is your rotated coordinate shear strain, and this is your original configuration strains given here, and then sine theta. This is what you see in our stresses also. Have done the same thing. Finished developing equations for epsilon x dash, epsilon y dash, and gamma x dash y dash, right? Or one we wrote as one. Here we will represent what happens in stresses and what happens in strains. How are they related? If you see, epsilon x1 we just formulated is epsilon x plus epsilon y by 2. Why did not we found epsilon y1? Epsilon y1 can be found substituting. Remember, we did it for shears also, substituting, sorry, theta plus 90 or theta with theta plus 90 in epsilon xy formula. All right, that's why sigma y1 is epsilon y1 is not necessary to separately determine. You can do it. We have done it for shear stresses. We have done it for normal stresses. We can do it for normal strains also, the same assumptions, not assumptions, same thing. Okay, so if I look at these two formulas, epsilon x1, gamma x dash, right? Sigma x dash, epsilon x plus epsilon by 2, gamma x plus gamma y by 2, epsilon x minus epsilon y by 2, gamma x minus gamma y by 2, cos 2 theta, sorry, not gamma, this is epsilon y, this is sigma, gamma xy by 2, tau xy sine 2 theta. Remember, the change only is here. The change here is because this gamma xy is engineering strain, but gamma xy by 2 is tensorial strain. Okay, so it's in tensorial format. Again, here gamma xy by 2, you get tau x dash y dash. Okay, same formula, same formula. So therefore, if I write epsilon x1 plus epsilon y1 should be equal to epsilon x plus epsilon y. That is what we found for stresses also. So here is the relationship, right? Epsilon x goes to if sigma x goes to epsilon x, sigma y goes to epsilon y, tau xy goes to gamma xy by 2, which is equal to epsilon xy in tensorial state. Same thing, sigma x1 goes to epsilon x1, tau x1 y1 goes to gamma xy by 2, which is equal to epsilon x1 y1. So if instead of gamma, if you write, you can write epsilon x1 y1 here. Okay, you can write that. So that's the relationship between. So if you remember one formula, you can do it for both. And therefore we can find the normal, maximum normal strains and the planes and maximum shear strain also based on the same formula that we can found for stresses. So remember, for stresses, maximum stresses, sigma max and sigma min is given by sigma x plus sigma y by 2 plus minus the radius. So this was the center plus minus the radius, right? Here also, this is the center plus minus this is the radius. Only replacement will be, instead of tau xy, you have to write gamma xy by 2. That's the only change. The plane, the angle of the plane is 2 gamma xy by 2 tau xy by sigma x minus sigma y. In shear, that is going to be your gamma xy by epsilon x minus epsilon. So 2 tau xy becomes gamma xy because there is a factor of 2 if you see. Okay. All right. Now for tau max, that means shear stress maximum is the radius itself. Here also gamma x by 2 maximum is going to be the radius itself. So that is equal to, again, epsilon x1 y1 max or epsilon xy max. Okay, and average is going to be given by sum of the stresses by 2, and that is constant for any directional strain you take, any direction of rotation you take. Okay, so principal strains and principal stresses occur in the same direction. So where the stress is high, strain will also be in the same place, right? High. Okay, let's look at a simple problem. If you have any question, you can ask. I'll pause for. So let's solve one problem. Very simple problem. So here is an element given. Okay, the original element is this, the blue colored one, and its units, its length are given 1 and 1. Okay, length and width or breadth, whatever you want to say, is 1 and 1 given, and its strains are given. Epsilon x is 340 into 10 to the power minus 6. Epsilon y is 110 into 10 to the power minus 6, and gamma xy is 180 into 10 to the power minus 6. If I have to draw that element, how do I draw the deformed element? The deformed element, I have to, in x, I have to give 340, right? That is given. So I'm just giving this. Let's say this is 340 in exaggerated format. Epsilon y is also positive, so 110 on the upper side. So this is my thing. Gamma x is 180, right? So I'm giving gamma xi in one direction. So one rotation along 180. Once you know gamma xy 180, you know what will be theta, right? Tan inverse of gamma xy. Almost same value. So this to this, there is an angle. So you draw a line here like this, which is elongated by this much amount, small amount. Then draw a parallel line to this, right? And then you have this line already, right? And then join this length and this length should be same, and then join them. So this is a deformed, deformed element in the xy plane. Okay. Now what is asked? It has asked that the strain for the element are oriented at an angle 30. So angle 30, what would be the strains I have to find? Then I have to find principal strength. Then I have to find maximum shear strain. Okay. All right. And everywhere you have to show the oriented elements, properly oriented element sketches you have to draw. Fine, very good. So for that, what I need to find is I need to know epsilon x plus epsilon by 2, epsilon x minus epsilon y by 2, cos 2 theta, sin 2 theta, and gamma xy by 2. Similarly, for gamma xy, we will need the same thing, right? So let us find that. What is epsilon x given? Epsilon 1 is given. So epsilon x plus epsilon y by 2 is going to be 340 by 110 by 2, that is 225. And epsilon x minus epsilon by 2 is going to be this minus this by 2 is 115. And gamma xy by 2 is 180 by 2 is 90. Now I am not giving into 10 to the power minus 6. I am just writing micron. Okay. This micron means it is 10 to the power minus 6. All right. Okay. All right. Now I have to find in oriented element what would be the, so my oriented element is angle 30. So this is my new x coordinate and y coordinate. Right, these are my new x coordinate, which makes an angle 30 degree positive, that means anti-clockwise with respect to your original xy coordinate system. So epsilon x dash is going to be this. I have to just put the values because I've already found those values, and if you put, you get 360, right? Similarly, gamma xy I can find, and since epsilon x1 plus epsilon y1 is equal to epsilon x plus epsilon y is equal to 450, I can find epsilon y1, but just putting this, right? Epsilon x1 is obtained from here. Epsilon x, epsilon y is given, so epsilon y1 is obtained from this, so 90. Okay, these are simple calculations. Now 360. So what I have to do is along this line, I have to draw first an element in xy plane, x dash and y dash, or x1, y1 plane. This is my element. Now that element is elongated. Let me draw it. Okay, that will help us. This is my x1. That is my y1. Please pay attention to drawing here. So that's my element, right? This is my original element. One. Okay. Now it has deformed. The deformation I have to find along x1. So along x1, what is the deformation? Along x1, it is 360. So I'll go to 360 from here. Let's say this is my 360 point. Okay. Along y is 90. That is also positive, so upward, right? So let's say 90 is here. So that much is 90 micron. Okay. So this is epsilon y dash. This is equal to epsilon x dash or x1 y dash y1. Now gamma xy, right? Minus of 110. Now minus of 110 gamma xy meaning it is which directional rotation?
Clockwise, sir.
Clockwise rotation. Now clockwise rotation I have to either give, but here it is given anti-clockwise. Why anti-clockwise? Did I do it correctly? Can you do some calculations here, someone, and quickly see is it positive or negative? No, it's negative. Sorry, it's right. It is negative. It's right, negative. So positive shear strain is given by change in angle inward, right? Okay, and negative shear strain will be given by change in angle outward. Remember, because the angle when gamma xy is positive, the angle will be lesser than 90. When gamma xy is negative, it will be more than 90. So earlier it was 90. So now it will change to more than 90. So it's going to be on this direction. So let's say this is my gamma xy. So this is my new point here, and that I'll draw parallel to this. Parallel to this, I'll draw something like that. It will come, and this will be parallel to this line. So it goes like that. So this is my deformed geometry. Okay. Now, some of you may say that, sir, why did I draw only on one plane? You know, gamma xy as one side. I could have drawn gamma xy in both sides. Yes, you can. Divide it by 2. One side you extend this, one side you extend that. Gamma xy by 2 here, gamma xy by 2 here. So those probably we will be doing in some other example. Now, how do you find principal plane? The angle for principal plane. So that part is done. So first part is done. Second part is to find principal planes, right? So theta p, you can use the formula and you can put them. So you get two angles, right? You know that principal planes, one will be the maximum, one will be the minimum. So 225 and plus minus 146. So the maximum is going to be 370 and the minimum is 80. Okay, clear? So maximum and minimum occurs in 90-degree difference of angle, if you remember the Mohr circle. So this is my 370 and that's my 80. And both are positive, so both are going to be elongations on both sides. There is no shear strain in maximum principal planes, right? And therefore, I don't have to rotate it. I just have to draw parallel lines to your x1 and y1 plane. So this is your deformed element. All right, clear? Next one, shear strain, maximum shear strain. Okay, maximum shear strain is same as the radius of the Mohr circle, so it's going to be this formula: epsilon x minus epsilon by 2 whole square plus gamma x by 2 whole square. So if you do that, you get 146. You calculate it by your own hand, maybe 146, maybe lesser than that, maybe around 145 point something. And theta is the plane at which the maximum shear acts is plane of maximum normal strain plus 45 degree. You remember from your shear stresses, and that's going to be 19 plus, here it is 19, remember, 19. So 19 plus 45 is 64. Gamma xy at 64 degrees minus 146 pi. So the angle, the value comes as, sorry, the sign comes as minus 146. Okay. Now minus means it's making more angle than 90 degrees, so it's not squeezing in, it is outside. So this is your, and at that value you will get your sigma average values will be your strains. So sigma average, epsilon average is this one, 225 here and 225 there. So you elongate this one this way and you elongate this one this way. So this is the one, and then you rotate, right? This line you rotate, comes here, then you draw a parallel line and join it with your x1 axis. So that's your deformed geometry. Please do them yourself at home, and if you have doubt, get back to me. Okay, with that I'll stop. Let's say, let's say that you wanted it to have both sides shear strain. So how would you draw it? So what is the plane? 64, right? So 64 is going to be something like this. This angle is 64. Okay. Now, what do I have here? I have, this is my element, let's say. This was my original element in the transform coordinate, and my deformations are given by sigma average is 2 to 5, right? So 2 to 5 here. So let's say this is my 2 to 5. Here also I need 2 to 5, right? So this is also 2 to 5. Now gamma xy is equal to 292 minus 292 micron. So gamma xy by 2 is going to be minus 292 by 2, which is equal to how much? 146, right? Is that clear? Is that right? Check it. So now what I'll do is so this is negative, right? So both side 146 negative. So I'll draw 146 here and I'll draw 146 there. Okay, right? So let me draw 146 on this side. So this is my 146. So what I'm doing is I'm rotating this line by this way 146 degree. So this is your 146 into 10 to the power of minus 6. Okay, So this much is gamma xy by 2 equal to 156 negative. Similarly, I will rotate this line in this direction by 146, right? So that comes out to be, let me rub this for the time being. That comes out to be, okay, up to this maybe. So this is also xy by 2. Okay. Now I have to draw lines. Okay. Now drawing, you see how difficult it will be to draw it if I do change in both sides. I have to draw one line that is parallel to this and another line that is parallel to that, and that's not going to be easy for me to do. Okay, so something like this, something like that. Oh, it's not going actually that side. Fine. So something like this and that. So that is your deformed geometry. Okay. Let me try to draw it. Yeah, I could draw it, right? So this is my deformed geometry. If I go both sides, and if I go only one side, this is enough to draw. Either of this you have to draw when you do transformation or when you find strains at a different orientation.